All right, the second half of areas and lengths and polar coordinates. And we're going to do 3 examples with areas inside parts of polar curves and areas enclosed by intersections of polar curves. And so we'll have lots of tools that we'll need to set up, and we'll need a lot of understanding in how these curves are actually graphed. So the first thing we're asked to do is find the area of the region enclosed by one loop of the curve r squared equals sine 2 theta. That's a lemniscate, if we remember from previous videos and just experience in general. So with r squared and sine, we know that we're in this angled one right here. The reason we might know that is that at pi over 4, theta is pi over 4, 2 times pi over 4 is pi over 2. Sine of pi over 2, that's maximum. That's a maximal value for sine. Pi over 2 is, because sine of pi over 2 is +1. That's as big as this would get. So we'd be at plus or minus 1, which would be one tip or the other. And that was, of course, at the angle pi over 4. So we know that this thing has this form right here. So lemniscate, angled along or oriented along the line pi over 4. The pole and pedal points that we need to find are done the same way that we've done in the past. R is 0 or R is 1, right? Or this function here is at a maximum value, which is +1. Note that it can't be -1 because r squared isn't equal to -1. There are no real radial values that correspond to r squared equals -1. So doing this in the same fashion as usual, the pole points are sine 2 theta equals 0. That's when 2 theta is equal to any positive multiple of pi, or sorry, any integer multiple of pi, positive or negative, and we get theta is equal to pi over 2k, just from simplifying this. So pi over 2k, and k is 0, we get 0. K is 1, pi over 2, k is 2, pi, and so on. We could go in the negative direction as well, to negative pi over 2, whatever might be useful. Okay, there are also more than one way to set up this integral correctly too, so note that. Sine of 2 theta equals 1 to find the pedal points, the points where we're maximally distanced from the pole. That's when 2 theta, this argument, is equal to pi over 2, and then it's any time we come back around to that, plus 2 pi k. So solve for 2 theta by dividing 2 on both sides, and we've got pi over 4 plus pi k, and that gives us a whole family of angle values. Pi over 4, 5 pi over 4, 9 pi over 4. If we went to the left, we'd have a -3 pi over 4, so on, if we were to need that. We can almost always do this in terms of positive angle values, so we might as well just stick to those. Now they say enclosed by one loop of this curve, not two, so we want to keep that in mind. Now, one loop travels from 0, 0, so this is r equals 0, sorry. The angle is 0, gives us a pole point of 0, so there's that. We have a pedal point of pi over 4, right? That's our first one. Comma 1, or 1 pi over 4 gives us that pedal point. And then at pi over 2, we're back at the pole. So we travel from 0 to angle pi over 4 to angle pi over 2, and we've done this loop in that process. Now, keep in mind, we've also done these two loops, or all these loops simultaneously as well. So let's be careful with that. We don't really have to worry too much. Students like to ask, well, aren't we finding twice the area if we do this one and it's forming at the same time as that? Well, we're not adding the negative sign. If we were to solve for r here, it's plus or minus square root sine 2 theta. We're not using that negative square root of this to add in this area on the other side. We're not using the reflected portion of this. So we're not adding double the area when we do that. It's hard to kind of see that that's the case. So after we've done this example, you should just understand that, or just accept that for a lemniscate, you don't worry about the fact that this thing's drawn sort of simultaneously. We're not finding twice the area. Now, part of what's interesting about that is the fact that in the formula for the area, they ask for r squared. Well, when we look at the equation of this curve, r squared equals sine 2 theta. So those things kind of coincide in a very similar way, and we end up just writing sine of 2 theta. So in this case, be sure not to square it. We don't need to square it. We already know what r squared is. It's sine of 2 theta, as we see. Now the 1/2 is just part of that area formula for area in a polar curve. And then d theta, of course, is the rest of that formula. And we now know that from angle 0 to angle pi over 2, we form this pedal, or this one loop of this limit. So here's our limits of integration. Sine of 2 theta, that's going to take a u substitution, u equals 2 theta if need be. Or you can be just tricky with a sine 2 theta antiderivative there. But ultimately, you should come out to 1/2 when you're done with the details of this definite integral. Okay, of course, the setup is always the harder part in these, but we certainly don't want to forget to take our time and be careful here. So confirm that that answer is correct, and we'll move on to the next one. Find the area of the region that lies inside the first curve and outside the second curve. So first curve, second curve. First curve is a limacon, second curve is a circle. Radius 1 for the circle. Specifically, this limacon, a over b, a is 1, b is 1. This is a cardioid, 1 over 1. So we know that we're dealing with a cardioid specifically, and a circle. This circle is centered at the origin. So we see that drawn down here. For the limacon, a nice way to graph a limacon is to just graph the quadrantal angles. I don't think we've done that explicitly yet. We've seen that in a graphing utility, but to graph these by hand for a limacon, you can just do 0, pi over 2, pi, 3 pi over 2, and 2 pi. And that should pretty much steer you in the right direction each time, especially a cardioid, which doesn't have an inner loop, so there's not so much detail that you need to be careful of. Now, before we try to draw this thing, though, let's go back and find the intersection points. Set the first curve equal to the second. 1 minus sine theta equals 1 then. Subtract 1 from both sides, so sine theta equals 0. Solve for theta. Theta is 0 plus pi k. So in other words, theta is any whole number multiple of pi. 0, pi, 2 pi, 3 pi, negative 2 pi, so on. Hopefully we'll only need some of these positive angles right here. So when we go to plot this, we realize, okay, 0 and pi should stand out. 0 and 2 pi are coterminals, so we probably don't need 2 pi. And then we'll note that, yeah, okay, when we plug in 0 to the first curve, or the second curve, r equals 1, well, that doesn't depend on theta, so we just get 1 out. So 1 0 is on this circle. When we plug in pi to this curve, well, that also doesn't depend on theta, so 1 is also what we get. We get pi, or 1 comma pi. So we've got this point and this point as our intersection points. And to sort of get an idea of what the cardioid looks like in this graph, we just put these 4 or 5 quadrantal points down. 0, 1, or 1, 0 for r theta, pi over 2, 0, or 0 pi over 2 for r theta. And that's actually down here. And then 1 pi for r theta, 2, 3 pi over 2 for r theta. This is the one that stretches or elongates a little bit. And then we're back at 1, 2 pi for this last point. So we've made a full lap around this. Now they say inside the first curve, but outside the second. So here's the first curve inside this, but outside the second curve. So this area right here that we sort of hashed in is the region that we're trying to find the area of. Now, it's not as hard as it looks. Polar coordinates give us a really nice tool to do this. What we'll do is we'll calculate the area from here to here of the outer curve, 1/2 r1 squared, minus the area contained inside here, 1/2 r2 squared. This should be somewhat similar to some of the area between curves that we did back in a few chapters ago. So r1, that's 1 minus sine theta squared. And then r2 is just 1 squared. And this is just a matter of simplifying, combining like terms, getting yourself into a position where it will be easy to find the antiderivative. And this looks like it's a good spot for that. Be careful when you do square this out. There should be a middle term. There should be 1 minus 2 sine theta plus sine squared theta. So be careful to take your time with that. Um, and we see down here that this is ready to be integrated. Antiderivative of sine theta is cosine theta, so that's, or negative cosine theta, but that minus sign helps or cancels out. And then sine squared theta, just recall that it's antiderivative from our first chapter in this course, comes out to this. If you need to work through the details of that, then go ahead or double check it. Absolutely do so. And then we're going from pi to 2 pi. That was one thing I didn't quite touch on when we set this integral up. We go from here to here because we're only worried about the area that's swept out along these. Inside the limacon, but outside the circle, right? We're not worried about any of this area because it's not outside the circle. It's not outside the second curve. So anyway, whatever this is equal to, I'll leave that up to the reader. It's just applying the limits of integration to that function. We should see some positive area come out of that. Okay, and a third one, just focusing again on the setup for these. Find the area of the region that lies inside both curves. R1 is 1 plus cosine theta. R2 is 1 minus cosine theta. Now notice these are limacons, A plus B cosine or sine theta. And we see 1 and 1, 1 and 1 for coefficients. The absolute value of their ratio is 1, so these are both cardioids. Once again, might be a good idea to try to graph these things, but before we do so, where do they intersect? Set them equal to each other. First curve equals second curve. Subtract 1 from both sides, we get cosine theta minus equals negative cosine theta. Well, then add cosine theta to both sides, so we have 2 cosine theta equals 0. That just means cosine theta equals 0. And then solve for theta in this equation. These are all the pi over 2 and pi away from that angles. So pi over 2, 3 pi over 2, 5 pi over 2, so on, or also in the negative direction as well. And again, hopefully we'll only need a couple of these and not all of them as indicated right here. So what do they look like? Write our quadrantial angles down. We don't have 2 pi this time because we know that 2 pi is the same as 0, particularly in these limacons. So R1 gives us 2 because 1 plus cosine 0 is 1 plus 1 is 2. 1 minus 1 in this case is this 0. And continue on for the rest of these, and you see that these are 2 cardioids. R1, let's see, radius 2, angle 0, that's right here. So this is R1, the first limacon in red, and then the second limacon is in black, and 0, 0, that one starts here, and they intersect at these pi over 2 and 3 pi over 2 angles. So we know their points of intersection. Oh, they also seem to intersect at the pole. How might we have known that that's true? Well, that probably occurs at an angle of pi over 2 or 3 pi over 2 somewhere down the line. Because it doesn't matter which angle. Sorry, the second curve R2 hits 0 at some point. The first curve R1 hits 0 at some point. It doesn't matter what angle got them there. They're at the pole, so there's no distance to move. So they're stuck there no matter what their angle was. So we do have a third intersection point thanks to that. And that does notice that occurs at non-pi over 2 angles. But it's not in polar coordinates, it is an intersection, and Cartesian coordinates, it would not be an intersection, it didn't come out something like this. But anyway, we never think about these things in Cartesian, so we're fine to think of it as is. Now, we need to find the area that lies inside both of these curves. So we need the area in here and the area inside of here. Each of these little crescent-shaped pieces, or sort of football-shaped pieces. Now, let's just find the area inside one of them, and we'll double it. That'll make life a lot easier. Now, what is this point for R2? That's a pole point. That's when the angle theta is 0. So we can go from the angle theta being 0 to when the angle of theta is pi over 2. We're here, and that should be a distance 1. See that? So 0 to 2, 2, 0, and then 1 pi over 2. And then to get back to 0 again for R1, or sorry, for R2 rather. This is here and here is this first point on the graph, and then here and here for that second point on the graph, and then 2 pi is the next one, but that, so we don't want to be inside that curve though, so we want to be very careful about that. So what's actually happened is we can only get the area from this point to this point, and as it's swept out along this curve. That's all I've been able to describe so far. Okay, we won't worry about the area in red because these two cardioids are essentially identical from each other. This side is symmetric to that side. We don't want to assume symmetry all the time, but this is a problem where it really helps us get out of a bit of a mess. So now, if we can just get this little sliver of area right here, and then we can quadruple it, then we'll have the area in all 4 of these little sort of crescent nail looking things. So let's see that down below. We're going to take, we're going to double the area, which is the area in black plus the area in red. The area in black, again, that's from 0 to pi over 2. That's for R2, or R1 rather, the red curve. Okay, and that's going from, so zero to pi over 2, 1/2 times 1 minus cosine theta. Right, so that's this R2 curve, 0 to 1. So we're going 0, 0 to 1 pi over 2 is here. So angle 0 to pi over 2. And this is R2, the black curve. So it's 1 minus cosine theta for R. Square it times 1/2 d theta, and that's our area in that little sliver. So we are going to just double these things when we're done. We'll find that just, being careful and not assuming symmetry, in this red curve, we go from pi over 2 to, that might be pi. Let's have a look. For R1, the red curve, we'll go from here to here, pi over 2 to pi, yes. And we'll go from here to here, sweep that out in the second quadrant, pi over 2 to pi, and then 1 plus cosine theta squared times 1/2 d theta. So after some very careful, possibly confusing setup, we will pause and have a look and make sure that that does make sense. The red curve draws out its little sweep, or its little sliver of area from pi over 2 to pi, and the black curve in that region goes from 0 to pi over 2. And you can kind of see that by the, the quadrants that those things are in, those little slivers are in. Now, I'll leave the details of this to the reader. Be careful squaring this. It's 1 minus cosine theta is going to be 1 minus 2 cosine theta plus cosine squared theta. Another thing to be careful of, these limits of integration are different. So it's not a good idea to combine these integrals into one integral. You could run into some mistakes. If you did so carefully, that would be fine, but it's probably more work than it's worth to do so carefully and correctly. So calculate each of these. What you should find is that it should meet intuition. Each of these two areas should be the same. So we could have just done what I said before, which is quadruple this 1/4 of all these. So far, these two integrals make up this half of the area. And we just double them to get this other half. And that's what the formula that I've sort of set up here is telling us to do. That's why we have a 2 sitting out front here. Double this answer when we're done to have the full area enclosed by both of these curves. I think it would be an excellent exercise for students to set up the integral for at least one of these two down here and make sure that it matches one of these two values, and you fully understand how to set this problem up, not just find the answer that's left for you to find down here. So it is a bit of a delicate affair to come up with the integral formulas for these areas. You can see that the hardest part is choosing the limits of integration. It could even be tricky to understand when they say inside one curve and outside of another to know, subtracting things. So if it's outside one and inside another, then you're going to want to do, this is the inside curve, the curve that you want to be inside of. This is the curve you want to be outside of. You want to get rid of the area that it contains so that you're looking at the region outside of it. Other than that, I think these things just take a good bit of practice and a little bit of remembering how to take antiderivatives of squared trig functions, possibly trig functions to higher powers, and then evaluating those integrals carefully. So lots of practice should make this seem doable. Good luck with that.